Okay, this should hopefully be a relatively quick video about factoring. We're going to talk about kind of the standard procedure for factoring every possible problem, and then get into some detail about the different types of factoring problems you might encounter. So difference of squares, perfect square trinomials, and some of the trinomial factorization problems where you have non-leading coefficient. The leading coefficient is not 1. So let's get into that. Basically, though, the first step of factoring, no matter what, is to take out what you can. So if you have that's what's called a greatest common factor. So if each term that you're factoring has something in common, the first step would be to take that out, factor it out of each term. After that, check and see if it's an easy problem. What that means is if, generally speaking, perfect square trinomials and difference of perfect squares, those are easy. There's also something called sum or difference of squares, and sum or difference of cubes, and we'll look at that at the next slide. And then there's some grouping strategies you can do. So if you have a really strange looking problem, what you can do is group them into 2 and 2, and that might help you. Or you can group them 3 and 1 or 1 and 3, and that will kind of illuminate the way forward, because you might have, for example, a perfect square trinomial and a perfect square, and you're subtracting those two things and you end up with a difference of squares. So let's dive into some examples here. Actually, before that, here's some special cases. This just illustrates specifically what those easy scenarios are. So when we could have perfect square trinomials, difference of squares, or difference or sum of cubes. Now we get all of this information just from multiplication. Just from when we multiply polynomials together, the advanced distributive property, or just the distributive property multiplication. And so, for example, like perfect square trinomials, what that means, if you have a plus b quantity squared, that's the same thing as a plus b times a plus b. And so if you multiply these out, you would have a squared plus ab plus ab, right, plus b squared, which is a squared plus 2ab plus b squared, which is where we get this. Okay, same thing if you had a minus b quantity squared. Difference of squares, when you have an equal sign, that means both sides of the equation are equal to each other. So multiplying these together gives you this, but the two things that had to be multiplied together to create this product right here were these two factors. And we can sort of look at that if we do a real basic example of a difference of squares problem, we say like x squared minus 9. Another way that's okay for us to write this is x squared plus 0x minus 9. And you probably have learned this before, but if you're trying to factor a trinomial, what you're looking for, especially if the leading coefficient here is 1, is what two numbers multiplied together to be this negative 9, but add together to be this 0. And if you're thinking about that, well, the only two numbers that multiply together to be negative 9 and add together to be 0 would be plus or minus 3, positive 3 or negative 3. So you would say x squared minus 3x plus 3x minus 9. So that is why this negative 3x and positive 3x add together to be 0, so x squared minus 9. So so that's kind of how we can sort of that's how we know that this is how the factorization works. If we didn't just, sorry, I kind of went the wrong direction there. If we continued out to factor this and we took out a GCF from the first two terms and the second two terms, clearly we would have x in the first, and left over we would have x minus 3. And if we took out a 3 from the next one, we'd have x minus 3 left over. Then you can factor x minus 3, x plus 3. So that's how we get to this typical way of doing the difference of squares problems. Difference of cubes and sum of cubes, really what that comes down to, honestly, is memorization. Those are a little more difficult to just naturally see, but if you did distribute this out, you would end up with just that. Okay, so moving on to some examples. So first step is to take out a GCF, right? We have these two terms. In common between the 6 and the 8 is a 2, and in common we have an x and an x and a y and a y. So if we took out a 2xy, well, what would be left over from this? It would be 3. What would be left over from this? It would be negative 4y. So that's how you factor just a simple polynomial like that. This one is a little more tricky because there's more stuff to it, but again, we can say, okay, what's in common between a 12, a 6, and a 6? A 6. What's in common between x squared, x cubed, x to the fourth, and x squared? An x squared. and look at the y's. What's in common here? Y cubed, y cubed, y cubed. They all have y cubed. And what's the common factor, or what's the GCF? Like, what's the z term? What's the most common, the largest possible z we can take out? Z to the fourth, the z cubed and z squared. All of them have at least z squared. So then if we take x times 6 times x squared times y cubed times z squared out of this first problem, we're left with 2 z squared minus, we'd have x squared z, and then plus, let's see, we would have, we just have 1 right there, right? Because that term there is the same as that term there. So that's how that factors. Now, how do we know if we're done factoring? Well, one thing we need to look at is there only multiplication shown between our two, like our main things? Not two, it could be more. So we have, this is all multiplication, and then this whole thing here is times this whole thing. It's okay if inside the parentheses there are things other than multiplication. That's fine. So that's check number 1. All we have is multiplication. That's great. Now, we also have to look at, in terms of, in parts of our factored, of like our running solution, is there addition and subtraction? And if so, are we dealing with exponents that are greater than 1, right? And if we are, then there's a possibility that something can be factored. This particular problem, no, you can't factor this any further. There's no point. You could take out a z from the first 2 terms, but that doesn't do anything to simplify it. So in this case, we're done with this problem. Okay, here's a really basic trinomial factorization problem, and one way to think of this is what two numbers multiply together to be 12 and add together to be 7, and you should see right away that that's 3 and 4. A little bit more of what's going on here is we're not looking for numbers that multiply together to be 12, we're looking for numbers that multiply together to be the product of 12 and the leading coefficient. So it just so happens that the leading coefficient here is 1. I don't know how I wrote a 4 there. The leading coefficient here is 1, so 1 times 12 is 12. That's why I want to know what two numbers multiply together to be 12 and add together to be 7. One way to think of this, I've seen this done this way, is you can write the middle term here, 7, or we can write the product of the first coefficient and the constant at the end up at the top of this x, and then write the middle term here, 7, and then what we have to do is what two factors of 12 will add together to be this 7. Well, it would be 3 and 4. And then what we would do is say, okay, it's x squared. We can bring down this plus sign. We said that 3 and 4 are the two numbers that we're going to get to add together to be 7. So 3x plus 4x plus 12. Then you can go, this is the whole process. This is not a necessary thing to do every time, especially if you know how to do this really efficiently. But the GCF between x squared and x is 3x is just x, so x plus 3. GCF between 4x and 12 is 4, so plus 4, x plus 3. Now the GCF between these two things is x plus 3, so we take x plus 3 out and we're left with x plus 4, which is of course what we have over here. So this one's a little bit more tricky now. We have a leading coefficient that's not 0, but the first step factoring is to say, okay, what's the greatest common factor? So here, this is 2 times 15, this is 2 times 2, this is 2 times 24, right? So I can take a 2 out of all of these things. And if I do that, I'm left with 15w squared minus 2w minus 24. Okay, now, what I need to do is, effectively what I need to do here is think, okay, what two numbers multiply together to be 15 times 24 and add together whatever 15 times 24 is, which should be, probably should have prepared that. We have 24 times 5 would be 220 plus 360, right? What two numbers multiply together to be 360 and add together to be 2? Well, that's not a super easy question to answer, is it? So what we can do, one way to do this would be to say, all right, what are the factors of 15? Well, 1 and 15 make 15, 3 and 5 make 15. Same thing with 24, 1 and 24, 2 and 12, 3 and 8, 4 and 6. Those are the different ways I can get 24. And so I could take a pair of these numbers. So I can take, for example, the 5 and the 3 and say, okay, that's 15, right? 5 times 3 is 15. And I could take the 3 and the 8, that's 24, 15 and 24, right? Can 15 and 24 ever go together to be -2? No. So that combination doesn't quite work, but we could also check the other way around and say, okay, what if we did 5 and 8? That would be 40, and 3 and 3, that would be 9. That's not going to work either. So then let's say, all right, well, it wasn't that, so maybe it's 5 and 4. So 5 and 4 is 20. And 3 and 6, that's 18, right? 3 and 6, oh, look. So 20 and 18 do go together to be -2 if the 20 is negative and the 18 is positive. So, okay, let's take this first term, 15w squared, and the minus sign. So I'm going to bring them down here, 15w squared and the minus sign. We had this 20, so 20w, and then we're going to add the 18w, right? That's going to give us this, that's going to give us that -2. And then minus 24. We take the last sign and the last term, bring them down. Now we do the same thing where we group. Remember, there's still this 2 out here, but we're kind of letting it be for now. The GCF between these first two terms is going to be a 5w. Left over is going to be 3w minus 4. And then between the 18w and the -24, the GCF is 6. So we're going to take out a 6, and we're left with 3w minus 4. And then we see, oh look, 3w minus 4 is in common, so finally 3w minus 4, and left over is 5w plus 6. And the last thing we need to do is say, oh, there was that 2 there that we took out originally, so that is going to be our answer. Alright, so here's a perfect square trinomial. Now how do you know if something's a perfect square trinomial? Well, what we need to do is check these 3 things. Well, we look at these 3 things to do it, to check 2 different things. First of all, is the final term, the constant, is that a perfect square? Or the coefficient of the final term, we should say. Is that a perfect square? 49? Yeah, it is. Is the coefficient, the leading coefficient, is that a perfect square? Well, 1 is a perfect square. It's 1 times 1. So that is. So check number 1, done. So last plus leading perfect square. Yes, okay, for this case it is. Second thing is, if we took the square root of this last thing, so 7, right, square root of 49 is 7, square root of the leading coefficient is 1, is this 14, okay, is middle term 2 times the square root of leading coefficient times the square root of constant term, or the last coefficient. If it is, those 2 check marks mean we have a perfect square trinomial. So 7 times 1 times 2 is 14. So this is a perfect square trinomial. So what we can say right away is that this must be x plus 7 quantity squared. Okay, this next one, right, same thing. Is 25 a perfect square, and is 64 a perfect square? Yes, okay, that's step 1. Then, is the square root of 25 is 5, right? And the square root of 64 is 8. So is 80 2 times 8 times 5? Yeah, it is. Now notice it's negative 80. That's okay, because we could potentially have plus or minus 5. I know that the square root of 25, if you're talking about principal square roots, is just 5, but negative 5 squared is still positive 25. So here we have an example where this is going to be, right, we have whatever this was squared, whatever the square root of this was, which was 8m, and then minus the 5 squared. If you were to multiply this out, 8m minus 5 times 8m minus 5, that would be your product. This would be your product. So this is the factored form of that trinomial. Okay, we often have difference of perfect squares. So here we say, okay, what's being squared? Here we can do substitution to say that these are all going to take the form of a squared minus b squared. So what's a in this case? Well, x squared is being squared, and then 4 is being squared. So if we wrote this out, because we know that it's a minus b times a plus b, then this would be x squared minus 4 times x squared plus 4. But notice that this again is a difference of perfect squares. So what's being squared here, x, and what's being squared with the 4 is 2. So just by the same reasoning, that would be x minus 2 times x plus 2, and then we have this x squared plus 4 left over. Now if we're factoring over integers or the real numbers, this is done. There is a way sort of to factor this, but we don't know how to do that yet. Okay, another problem. So again, what's being squared here? It was the 7x was being squared. What's being squared here? The 5, right? There was no GCF, so we don't have to worry about that. So by the same reasoning as before, 7x minus 5, 7x plus 5.